We've given this one before, but this will be my first time giving it. This will cover just the general basics of fiber optics. So let's get started. This is a registered continuing education program. InCab America has met the standards and requirements of the program. Credits earned on completion of this program will be reported to RCEP, and certificates of completion will be issued to all participants. There is a little bit of disclaimer. This does not include content that may be deemed as an approval or an endorsement by the RCEP. It just means that we've met all the requirements. The purpose of this course is to teach y'all what fiber optics is, how it works, and why we use it. We will describe its construction and discuss the underlying physics behind it, how it works, along with the electromagnetic spectrum. And we'll describe two key fiber performance factors, attenuation and dispersion. We'll discuss what attenuation is, what the sources are, and the limits for it. Then we'll discuss what dispersion is, the three types, and we'll review the three most commonly used types of optical fiber. And then to finish it off, we'll discuss two advanced fiber types, non-zero dispersion shifted, as well as the new G654 fiber. Learning objectives. After this class, we hope that you'll be able to explain what optical fiber is and its purpose, along with the three main components, the core, cladding, and coating. Secondly, explain the meaning and importance of total internal reflection. State the advantages of fiber optic versus traditional copper cables. Explain the meaning and importance of these concepts as they apply to optical fiber, Snell's law, index of refraction, and angle of incidence. Explain the meaning and importance of wavelength and frequency as they apply to optical fiber, and know those most used. Explain what attenuation is, what the sources are, and what the typical limits are. Explain what dispersion is, and what three types of it there are. And then name two newer advanced fiber types and why they are used. These are the webinar rules. We'll do a quick introduction here in just a second, and then the sound. Well, we've already basically done the sound check. The presentation itself should last about an hour, and then you can ask questions during the presentation, but I would prefer that you wait till the very end because that's when we'll do a quick Q&A. We'll do all the questions at once. Please try to keep those questions limited to the scope of this presentation. Just as a quick introduction, I'm Christian Riddle. I'm the project manager here at InCab America. I've been with the company for about 6 years, and then in the general fiber industry, I've been in for about 10 years now. This is my first webinar, so hopefully it's the first of many. So I hope that I'm able to teach y'all something about fiber optics today. So, in general, fiber optics is the technology that we use to transmit information using pulses of light through either glass or plastic fibers over long distances. And it works by having light constantly bounce from down the fiber, as it travels. And the method of that is there's kind of two components you can see here on this slide. Kind of the area you see here that's highlighted in yellow is what we'll call the core, and then this kind of gray field you see here is the cladding, and it'll bounce back and forth through it, from one end to the other. And the method of bouncing is referred to as total internal reflection, and it occurs in nature with light and just in general electromagnetic waves and sound and even water. And with light, total internal reflection occurs when light reaches a boundary between two mediums. And not only that, it has to hit at an angle which we'll refer to as the angle of incidence, and it has to hit it at what we'll call the critical angle, and we'll get into that a little bit later. And then light going from one dense medium to a less dense one. So here we have kind of two examples of that. We've kind of got one example here in nature And so we've got the medium of water and the medium of air above the water, and you can see the reflection of light as it bounces between both mediums. And then here we have kind of a more scientific kind of view, and this is light bouncing between the mediums in an acrylic rod. So why use fiber optics over copper cables? Um, well, the first reason is significantly less space. Fiber optic cable, when compared to copper, has much more bandwidth carrying capacity by volume. And so we kind of have a picture here to represent that. Um, you would need a very large amount of copper in comparison to fiber optics in order to carry the same amount of data. Reason two is bandwidth. It can go faster and farther than copper cable for a given bandwidth. And so the typical range of like a Cat5 and Cat6 cable is about 330 feet or 100 meters, whereas for fiber optic cable, you can get up to 90 kilometers. So the comparison is just, it's not even there in terms of distance. Some other reasons to consider. Uh, it's immune to electromagnetic interference and radio frequency interferences. So there's no crosstalk like there can be with copper cables. And it's also more secure. It's more difficult to tap. So how does it work? The key underlying principle here to remember is total internal reflection. And so what we see here is what we call the acceptance cone. And this is kind of the cone where light can enter and it will proceed to go through total internal reflection. If it enters outside of the cone of acceptance, it gets refracted and it's lost. And so you lose the data. So we'll get into a little bit more, I guess, complex theory here. So the underlying physics is we have two mediums. The core, which is the yellow field here, and the cladding, which is the gray field here. And what am I trying to say? The differences in refractive index is what allows the total internal reflection to take place. And the index of refraction is a way of measuring speed of light in a material because light moves fastest in a vacuum. And so here we can see kind of the equation for that. It's just the speed of light in a vacuum divided by the speed of light in whatever medium you're working with. That can be air, that can be water, and in our case, it's glass. In 1621, Willebrord Snell discovered the relationship between index of refraction and a medium, and this is how the groundwork for how fiber optics works. And so we have the index of refraction compared to total internal reflection. And so we have three examples here. And so if the angle of incidence is less than the critical angle, then the light will refract. If it is equal to the critical angle, it will kind of move in parallel. And then if it's greater than the critical angle, then it will reflect. And so light bends towards the normal when going from a medium from a smaller index to a larger index. And so here we have two different examples of that in a more. And so here you can see light is traveling through the acceptance angle, and the acceptance angle guarantees that the light will bounce at that critical angle and go through propagate through the fiber in that zigzag pattern. And then here we have the numerical representation of that. So now we'll move on to the basic types of fiber in our industry. So we've got multi-mode fibers and single mode fibers, and they're kind of split up into these different families. So we've got the OM1 fibers with the kind of larger core and cladding. And so the core is where the light goes, the cladding keeps the core, and then the coating, which is typically colored, protects the unit as a whole. And so we have multi-mode and then single mode. And then kind of as you move down the line, you get greater information carrying capacity. So light works on the electromagnetic spectrum, and light in particular for fiber optics works on a very particular spectrum, and we work on the infrared spectrum. And so, we've got the UV spectrum that's not visible to our eyes, and then the visible spectrum that we see every day. And then from there, we move into the infrared spectrum that we work on. The typical operating wavelengths, are 850 nanometers for multimode, 1300 again for multimode, and then once we move into the higher wavelengths, 1310 is the traditional standard single mode wavelength, and then 1550 is one we also see a lot, and then 1625 is also one we're also starting to see a lot more of. But you can basically operate in any space in the infrared spectrum for your fiber. These are just the more common operating wavelengths. What is a wavelength? A wavelength is the distance between identical points on a wave, and we typically express that in nanometers. There are low frequency and high frequency wavelengths, and high frequency wavelengths are shorter than low frequency wavelengths. You could even say even there's more energy. And so here we have a kind of visual representation of that. So there are two key performance factors when working with fiber optics. First one is attenuation. Attenuation is the loss of signal strength, and it's typically expressed in decibels. And there are two kinds of attenuation. There's intrinsic attenuation and extrinsic attenuation. And attenuation impacts the ability to reach the receiver with enough power. And so that's kind of like your range. And then in general, a 3 decibel loss in power equals a 50% loss from what you started with. So every 3 decibels is another 50% from what you started with. The second performance factor is dispersion, and that's the spreading out of signal pulses. So that's your wavelengths spreading out. And there are different types of dispersion. There's modal dispersion, chromatic dispersion, and then polarization mode dispersion. And this impacts the ability to decipher your signal pulses at the end. So we'll start with intrinsic attenuation. And so this is just loss of signal strength. And intrinsic attenuation is caused by impurities or substance within the optical fiber. Again, attenuation is expressed in decibels. And like we covered earlier, it impacts the ability to reach, so to make it all the way to the receiver. And so here we have fiber attenuation as a function of the wavelength. And so this is kind of like your starting attenuation for whatever your wavelength is. And so here on the graph we have the various things along the line that cause attenuation. So you've got Rayleigh scattering, hydrogen absorption, and then towards the very top, infrared absorption. And then here we display, which fibers are most affected by what. So intrinsic attenuation, think internal. isn't affected by outside influences. It's like its name, it's intrinsic to the fiber. And so the two forms of intrinsic attenuation are absorption. That's when a photon will give up its energy and excite an electron to a higher level. It's like a transference of energy. And then the second one is Rayleigh scattering, like you saw on the graph earlier. And that is light scattering as a result of defects or in homogenetics that are present in the fiber during production. These are very small, like microscopic imperfections that just happen during production. Extrinsic, think external attenuation. Macro bends is the most common one here. It's caused by like a large scale bend of the fiber. Um, and that's something you can see like with your own eyes. And this typically happens when you exceed the safe minimum bending radius of whatever fiber you're working with. And the loss is typically reversible once you remove the bend. It's not permanent. And so here you can kind of see how that happens. You know, when you bend the fiber, you affect that critical angle, and so once you reach a certain point, it you exceed the critical angle and therefore lose the light. Micro bending. So we have macro bending, and now we have micro bending. These are kind of smaller scale distortions that can be caused by various reasons. Some common ones are like fibers crossing over or crowding in a tube. And these are also reversible unless you have permanently deformed the cladding or the core as a result. Microbends are a little bit harder to work with than macrobends. And then here we have the impact of uh, of attenuation. So your the decibel loss. And then like we mentioned earlier, for every 3 decibel loss of power, you lose 50% of what you had before. And we have dubbed that the divorce law. Uh, Another topic we quickly touched on earlier was dispersion, and dispersion is the spreading out of light pulses. And the three main types of that are chromatic, modal, and then polarization mode dispersion. Modal dispersion, in which you typically see in multi-mode fiber, is the spreading of signal pulses as they travel down the fiber. So as they spread, they can also overlap. Um, and the overlapping can cause bit errors, and so you can kind of see a visual representation of that down here. And you know, when you're putting in multiple wavelengths, they're all bouncing in their wavelengths, but as they spread, they can start to overlap, and uh, that's what we call modal dispersion. Chromatic dispersion is the light spreading out as it travels um, through the fiber, and so as it slows down and changes speed, it will spread itself out. And so you'll start off with a nice tight wavelength, and then you'll kind of end up with a spread out lower wavelength. And then we have polarization mode dispersion. Um, Single mode fiber typically consists of one propagation mode, which in turn is comprised of two orthogonal polarization modes, and you can kind of see that down here. And then asymmetrical differences in the fiber introduce small index variations between the two modes, and this is called biorefringence. And it's caused by ovality of the core uh, due to your manufacturing process, uh, internal stress that can happen during cabling, and then external stress. Now, this wasn't discovered until the 1990s, and then um, as transmission speeds increase, combating this becomes very important. And so you can kind of see how stress and bends can cause the polarization mode dispersion. And so you have your orthogonal, um, you know, wavelength. here, and it's different from its partner, and this causes issues with the data. So dispersion in general leads to bit error, and so this top one here is what your theoretical input would look like. So 0, 1, 0, 1, 0, 1, and then this is what it looks like in the real world. So it's not perfectly, squared off. And then as your pulse broadens due to dispersion, you can still differentiate the zeros and ones here, but as it broadens, it can become harder and harder to discern the two. And so here at the bottom is an example of that. You can still kind of tell, but it's very muddy. It's not clear. And so you want to have something like these two. So how do we apply these performance factors? So attenuation, again, recall loss of signal strength. This attenuation is very much controllable by the cable manufacturing progress, and it can't get any better. It can only get worse. So if you start out with, 0.33, it can't improve. It can't go down to 0.32 during cable. It can only get higher. And then the typical maximum final values that we get for single mode at 1310 nanometers, we get 0.35, and then at 1550 you get 0.25. And then best practice in the industry is 0.34 and 0.20. The typical values for multi-mode fiber are 3.5 at 850 and 1.5 in 1300. In our industry, or in my experience, we don't work as much with multi-mode fiber, so best practice is kind of unknown. But as long as you're sticking to the typical maximum values, you should be okay. Dispersion. So, like we just discussed, it's spreading of signal pulses, and it is typically, it's overwhelmingly controlled by the fiber manufacturing progress, and so it's specified by whoever your fiber supplier is. And because it's mainly down to the fiber itself, it's not usually affected by your cable design or your manufacturing progress. Like we have here, it is what it is in a finished cable, unless you make your cable very poorly. And then there aren't really any finished cable limits for it. So as long as you're making good cable and you're getting good fiber, your dispersion should be manageable. And so now we have the advanced fiber types that we mentioned earlier on in the presentation. Increases in need for bandwidth and transmission distances have led to the development of two special types of single mode fiber. The first one is non-zero dispersion shifted, NZDS, single mode fiber. And if you remember chromatic dispersion, you can correct chromatic dispersion much like your glasses do, because you can kind of control how light bends, and that's the underlying fundamentals of your eyeglasses. And so the same principles can be applied to fiber. The two most common forms of that are Corning leaf and then OFS true wave. And then the standard for this is the G.655. It's designed for use with dense wavelength division multiplexing to boost the bandwidth. And then kind of a comparison to the data carrying. Standard single mode fiber can do about 10 gigabits and then up to 40 gigabits. And then the non-zero dispersion shifted fiber can do 100 gigabits and even more. So double and maybe even triple in some cases. And then it enables even longer distances. And so standard single mode, a maximum of 90 fibers or 90 miles. And then non-zero dispersion shifted fiber can go up to 250 miles. The other advanced fiber type that has been developed is cutoff shifted single mode fiber, or G654 fiber, and it's ultra low loss. Originally used for transoceanic submarine cables, the current fiber allows for even higher data rates, which go all the way up to to terabits, which is just an enormous amount of data per second. And it has even longer distances of up to 560 miles, and so it's kind of essential for connecting the world together and keeping us connected. It's optimized for use between the 1550 and 1625 nanometers, and it has some pretty great attenuation limits. The typical attenuation limits are 0.717 decibels at 1550 and 0.19, which, if you recall, the standard single mode had a typical attenuation limit of 0.25. So pretty great improvement. And an example of this fiber is Corning's TXF fiber. And then in closing, we have kind of a size comparison of fiber compared to some other common things. And so we have the optical fiber, just the glass without the cladding, fiberglass tile, and then human hair. So it's about the same size as human hair, which is kind of crazy to think about. And then you're probably thinking how you get your credits, because that's part of the reason you're here. Hopefully you're here to see me, but I understand that you probably want your continuing education credits. There'll be a quiz after this that will be sent out in a follow-up email, and you have to pass the quiz with a 70% or higher. Certification will be provided through the RCEP, and participation will be submitted after 1 business day. Recording of this presentation will be uploaded on our Learning Hub on our website. And then if you would like a copy of this presentation, please respond to the follow-up email and we'll make sure you get it. Thanks everyone for your time and attention. We'll open it up to Q&A now. Didn't quite take an hour, but more time for questions. Yeah, you're welcome. Michael Kruger, you're asking about splicing. Could you be a little bit more specific? Our fiber optic splices a repair option. Um, I would say in general, you can splice fiber as a repair option, but I guess it really comes down to what kind of cable you're using. Uh, Frederick, you asked, I thought multi-mode fiber had light bouncing from side to side, but single mode did not. Apparently that is incorrect. No, both fibers, it's propagating down or I'll go back to kind of the very first slide. It propagates in the same manner. Multi-mode is just, you have much more room in the fiber. Let me find the slide. So you have the core of the multi-mode fiber is significantly larger than the core of the single mode, and so you're able to put multiple wavelengths of fiber in the multi-mode, whereas for single mode you're just using one. So they both propagate in the same method. Multi-mode just is able to do it with more than one light wavelength than single mode at the same time. Uh, Justin asked, is there a way to go from Cat6 cable to fiber optic using a device connecting from one to the other and vice versa? Uh, I'm not sure. That's not quite my area of expertise, but we can definitely look into it and get back to you at a later time with that, regarding that question. Oh, got a lot of questions now. How do we determine the acceptance angle of a fiber optic? Um, uh, to be honest, I'm not entirely sure. I'll have to double check on that. That's another question we'll have to revisit. And we'll definitely answer your question. I just can't answer it today. Um, Aaron asked if bending of fiber cannot be avoided. Is there a certain bending radius that can be done to avoid loss of signal? Yes, and that bending radius is typically supplied by your cable manufacturer. Angus asks, is glass different for different fiber types, or is it just a size and cladding difference? Um, I would say it's typically just a size and cladding difference. Manufacturers may use different like glass qualities and have proprietary glass. Um, but when it comes to like if it's comparing single mode to multi mode, that's just sizes. Uh, Justin asked, are all fiber optics made from glass or can they use different materials? There are some fibers that are made using like plastics like acrylic, but in our industry, we typically only see glass as the medium. Uh, Mohammed Mustafa, what is the difference between G652D and G655? Uh, I don't know off the top of my head. We'll have to get back to you on that. Any more questions? Nope. I see Mike Riddle here has answered the question between uh, G.652 and G.655. Yeah, you're welcome, Michael. What is the difference between microband and macroband? Okay, let's backtrack a little bit. So macroband is like what you can like visually see. So, think kind of like large scale. Like I have a pen, so I can't really bend it, but I can bend it a little bit, and you can see that it's bending. So a macro bend is like more visual and more environmental, I'd say. Micro bends are very, very, very like small scale. So like uh, inside the fiber, the fibers are all in the tube together and they're bunched up, and so if some of them are crossed over and putting pressure on another, it can cause uh, bending in the cladding, which can push on the core. Um, some other things that can cause microbend or improper like coating on the cladding and uh, much smaller scale things. Any more questions? Example of finished cable bend radius. Okay, yeah, give me just a moment. I'll pull something up. Whoops. All right, so a good example of finished cable bend radius. So like our ADSS cables typically have a minimum bend radius of it's about we call it 15 times the cable diameter. So I've pulled up a design here that's the diameter of the cable is about point 520 inches, and so the minimum bending radius there would be 0.520 times 15, so about 7.8 inches. Would be an example of a real world minimum bend radius on a cable. Um, which one can occur due to wrong installation? I'm sure that's related to microbend or macrobend. Um, both can happen in one in installation, but I would say more common, you would more commonly see macro bending being an issue during installation. If a connector end was bad on a fiber optic, would it be possible to repair the connector instead of replacing the entire cable? Yes, absolutely. Uh, we do it all the time with our OTDRs. The connectors go bad, we have to cut them back and put on a new connector. So it's very possible just to replace the connector if that's what's going wrong with your cable. Do we need to make any fiber strain measurements after laying? Uh, that I'm not sure about. Uh, Mike, can you help answer that question? Could you use two connector ends as a means to repair a splice, like a female and male end? Mike, the question is, do we need to make any fiber strain measurements after laying? And then Justin, back to your question. In theory, you probably could, um, but every time you introduce a connector, you introduce more attenuation. Can some distortion and loss be overcome through software? Uh, yes. Um, so back on this dispersion slide, um, the acceptable pulse broadening can be overcome by software, but once you hit a certain limit, like the too much pulse broadening, software can only do so much. But software can be used to reduce bit errors. Questions about cable jacketing. I think that's a little bit outside the scope of today's webinar, but we can definitely help you with that question offline. Once you hit the max distance for the cable, do you just correct the signal and send it out again to the next path? You can use repeaters and boosters to continue, or yeah, but that's kind of a way of correcting the signal and continuing on. Is it possible to connect two fibers made of different materials? If it's like from glass to acrylic, no, you need to have a very similar index of refractions for that to be able to um, accomplished. But like if you're asking like from one manufacturer to another, there are fibers that are splice compatible with each other. But that's because they have a similar indices of reflection. Sorry. Can a repeater be used as a splice to resend the signal out to the second cable? I'm not sure. We'll take note of that and get back to you. Yeah, looks like Mike is saying yes, you could use a repeater in that way. Okay, well, we'll give it a couple more minutes for questions, and then I think we'll wrap things up a little bit early. Is diffraction an advantageous phenomenon in propagation in fiber? I'm not sure. I wouldn't think so. I think you'd want to keep your fiber as like your signal as intact as as possible, but as the question's written, I'm not entirely sure. Okay, well, I think we'll go ahead and wrap things up. If you guys have additional questions, feel free to email us with your questions. We're always happy to answer questions. I'd like to thank y'all for your time and attendance today. Uh, please do be on the lookout for the follow-up link. It will contain the quiz you need in order to get your PDH credits. And remember, you need 70% or higher, but the quiz shouldn't be that hard. Like we mentioned earlier, a recording of this presentation will be uploaded on our Learning Hub on our website at incapamerica.com. And if you would like a copy of this presentation, please just give us an email. We're happy to send you a copy. Thanks, everyone, and I hope you guys have a wonderful day. Bye-bye.